Hi, and here it is, the final question from this year's Gaokao math exam. I did a video last week on some of the multi-choice questions, and in the comments people were saying things like, yeah, that's great, but you should really check out question 19. Of course, it is very challenging, especially the last part, the final proof, but the first few parts are actually quite achievable. So we have this function f, defined on all the real numbers. F of x is 2 to the power of x for all x less than 0. We don't know what the right hand side of the function looks like, and it's going to change as we go through in parts 1, 2, and 3. Feel free to pause the video if you want to have a look at the whole question and have a try at it yourself. Otherwise, we'll go through step by step. So the question defines this capital D of x0, and what it is all real values of d such that f of x0 plus d is greater than f of x0. So we're thinking of d as being added to our x value, and what we want to do is add d, so we can either move right or left, such that the function value increases, so that's the y value increases. In question 1, we're given f of x is 1 minus x for x greater than or equal to 0. We want to find d of negative 1. So here's the graph, and starting from negative 1, we need to either move left or right, so we go uphill. So clearly we're going to need to move right. At negative 1, originally the y value is a half because 2 to the power of negative 1 is a half. So if I move to the right a little bit, say about 1 unit, then definitely I will be moving uphill. I have f of negative 1 plus d being greater than f of negative 1. In order to evaluate all the d values in the set, let's highlight the graph in the region where y is greater than a half, which is f of negative 1. I need f of negative 1 plus d to be greater than f of negative 1. So I need negative 1 plus d to be less than a half, because on the right over there, my function, my straight line, goes through a half comma a half. This means that d must be less than 3 on 2. And obviously, as we said, we can't move to the left. So what we have is d is greater than 0 and less than 3 on 2. So that is the first part of question 19. Essentially, that is testing whether we can understand the definition, this new definition that we are given, and apply it. For part 2, we're assuming that f of x is an odd function. So an odd function is one for which f of negative x is equal to negative f of x. Graphically, that means that if we reflect in the y-axis, we get the same thing as if we reflect in the x-axis. So then we can know exactly what the graph looks like, and it must look like this here. Now we want to prove that if f of x1 is less than or equal to f of x2, and neither x1 nor x2 is 0, we want to prove that capital D of x2 is a subset of capital D of x1. So let's start from the case where x1 and x2 are both less than 0. We must have x1 being less than x2 because we're told that f of x1 must be less than f of x2, and the function is increasing on that interval where x is less than 0. Now let's think about what d values would be in capital D of x2. So remember, in order to go uphill, I'll need to move right. I can't move left from x2 because I would be going downhill. I need to move right, but also I can't move too far because I can't move beyond the maximum there on the y-axis. So essentially, I can move any d value that is greater than 0, but less than negative x2. So x2 itself is a negative value. So for example, if x2 were negative 2, then I can move to the right just less than 2 units. If I go any further than that, I'm going to drop down into the part of the graph where y is negative and definitely less than where we started. Now that is a subset of d of x1 because from x1, again, I have to move it to the right. So d has to be positive. I can go as far as negative x1, and x1 is less than x2, so negative x1 is greater than negative x2. All right, that's just case 1 where x1 and x2 are both less than 0. Case 2, let's say x1 and x2 are both greater than 0. But again, because we've got an increasing function, it's going to be very similar to case 1. I won't write out all the details for that part. Case 3, and this is going to be the only other case, where x1 is greater than 0 and x2 is less than 0. We have to have it that way because remember, f of x1 had to be less than or equal to f of x2. So we couldn't have x1 being less than 0 and x2 being greater than 0. Now in this case, the d values in d of x2 are going to be very similar to case 1. So from 0 up until negative x2. But for d of x1, I can actually take any positive d value. I can go as far as I like to the right, and that function would approach infinity and approach y is equal to 0, always increasing. So definitely d of x2 is a subset of d of x1 in case 3. So there's part 2 done, and we're ready to move on to the final part. Again, it contains this idea of capital D of x2 being a subset of capital D of x1, but now that it's a condition given to us that we need to use to apply to prove some other properties. The other condition that we're given is that for x between 0 and 1, f of x has to be less than f of 0. The first part is to prove that f of 0 is greater than or equal to 1, and this is actually not too bad. I think the easiest way to do it is using a proof by contradiction. So we assume f of 0 is less than 1. And if we think about a diagram here, the graph is going to look something like this. It has to go downhill to the right because we're told that between 0 and 1, f of x is less than f of 0. So in order to make the contradiction, let's look at the graph we've got here. We're assuming that f of 0 is less than 1. And we know the function must go downhill directly to the right. We want to find an x1 and x2 with f of x1 less than f of x2, but d of x2 not being a subset. So if we let x1 be 0, we know we cannot move slightly to the right because we'll have to go downhill. So if we can find an x2 where we can move to the right and go uphill, then we'll be all good and we'll have our contradiction. So what we can do is choose x2 to be less than 0, where f of x2 is greater than or equal to f of x1. We know we can do that because we're assuming that f of 0 is less than 1. But we know that to the left, where x is less than 0, y is equal to 2 to the x. It actually approaches y is equal to 1 as x approaches 0. So we can definitely find that x2, and from that x2 we can add a small positive d value such that we move uphill. And so then that d value would be in capital D of x2. But if we were to add any small positive d value to x1, we'd have to go downhill. So that d, which we used on the left, is not part of d of x1, so therefore d of x2 cannot be a subset of d of x1. We have reached a contradiction, so that proves that f of 0 has to be greater than or equal to 1. So here we go for the final challenge to prove that f of x is monotonically increasing on the interval 0 to infinity. Essentially that means the graph cannot go downhill as we travel from left to right. Formally, it means there cannot exist any a and b with 0 less than a less than b, where f of b is less than or equal to f of a. We're going to again do proof by contradiction. So we're going to assume that there is such an a and b with 0 less than a less than b and f of b less than or equal to f of a. So how are we going to show that this contradicts the assumption that capital D of x2 is a subset of capital D of x1? Well, if, as in the diagram we have here, f of b is greater than 0 up here, what we can do is use b as x2. So if we let x2 is equal to b, and then take d as a minus b, so that when we add d or move d to the left, definitely the function is going to go uphill because we know that f of a is greater than f of b. This means this value of d is an element of capital D of x2. But if we choose an x1 way over the left over here, where f of x1 is less than f of x2, then if we move further left from x1, the graph goes downhill. So that means this same d value cannot be an element of capital D of x1. This contradicts the assumption that d of x2 is a subset of d of x1, which is good. But this method that I've shown here only works if f of b is greater than 0, because the left half of the graph gets infinitely close to 0. So if f of b is greater than 0, we can always find an x1 with f of x1 being less than f of x2. So this is only one case. We're going to have to do some other cases, and let's now look at another case. So we've considered what happens if f of b is greater than 0. So in the next case, and in all the other cases, we'll have f of b being less than or equal to 0. So for case 2, let's think about when f of b and f of a are both less than or equal to 0. What we can do here is let x1 be a, and then take d as b minus a. So moving across from x1, so adding d from x1 is equal to a, the function definitely goes down because it goes down to where f of b is. But we can choose an x2 on the left branch, so long as it's further left than negative d, then when we add d, we'll definitely go uphill because the function is increasing over there. So there we are again. In that case, we've found an example D, which is an element of D of x2, but not an element of D of x1. Okay, same idea with case 3. Now we're going to have f of b still being negative, got f of b less than or equal to 0, and now we're going to put f of a between 0 and f of 0. In that case, we can let x2 be equal to a and d be negative a. Moving left by d from x2 is equal to a gets us up to f of 0, which is definitely an increase, so that's good. But again, we can choose x1 to the left below x2, and moving d to the left definitely is going to be a decrease. For this final case, I'm going to make an additional assumption that f of x is less than 0 for x between 0 and 1. And the reason I can do that is because if f of x were greater than 0, then I could have just done case 3. I could have chosen an a value between 0 and f of 0. So it's only when I can't do that I need to go to case 4. And that additional assumption would help to get the contradiction in this last case. So I'm going to let x2 be 0 and d be equal to a. And then for x1, I'm going to go to the left over here. And to end up with a negative y value, I'm going to choose x1 as, say, a half minus a. A half just because it's between 0 and 1. So that when I add d, which is a, to a half minus a, I'll get to x is equal to a half. That will have a negative y value, which means that that d value is not an element of capital D of x1. All right, so that's it. It took 4 cases to complete the proof by contradiction, which I was a little bit annoyed about. I thought originally I could get it done in 2 or even 3 cases, but that's fine. If you have any comments, suggestions, if you have a link to a better solution, a more elegant solution, I'd be happy to see that, so please post a comment. In general, just to say that, yeah, it was a hard question, but it was really only that last part 3, part 2, that was really took a lot of thinking and a lot of work. I think the other parts were reasonable once you got your head around the definition. Although definitely, yeah, if I was a student sitting that exam under time conditions, definitely there's no way I would have got the answer to 3 part 2. But I imagine some students would have, some students would have got partial credit. And really that questions like that are really meant to give the really top students a chance to demonstrate their skills and hopefully, you know, earn their place at the top universities in China. I better leave it there. I think I've got a nappy to change.